All right, so in today's topic, we're going to be talking about Taylor series and Maclaurin series and what their purpose is. Like, what are we doing when we make a Taylor series or when we calculate one? And what is it? Well, let's say I had some arbitrary function f, and let's say he's really complex. Let's say it's just like, ooh, it goes like this, and then we sort of do some wiggles like here, and assuming that's not perfectly vertical, I made something that's at least sort of a function here. This would, of course, have an expression f of x. And let's say we wanted an infinite series to express this. So why would we want that? Well, as it is, the behavior that's causing this to do like that, assuming it's not a polynomial, it might be really difficult to take the derivative of this or the integral of it. And so what could be a really cool trick is if I'm able to write this as some infinite series of terms, and I wanted to take the derivative, I could just do the derivative of each individual term. Likewise, if I want to take the integral, I could just do the integral of each individual term. And so that can be very, very useful. Now, you have to pick a point about which you're going to do your Taylor series expansion. Let's call that A, so I can put that right here. So what would happen if I'm doing it about this point is that at first my expression would probably just look something like a straight line. So if I only had one or two terms, my thing would probably look something just like this, because the point of interest is right here is a, and so you could say that the derivative of that is weighted a bit. The value and its slope would be kind of weighted around this point. But as I add more and more and more and more terms, say 500 terms, I get something that will probably be a lot closer. So maybe something that, matches this really well, maybe it overshoots here, matches that really well, sort of does a dance around here, maybe goes up a little too high and then down and then kind of goes, oh, right? So as I add more and more terms, my infinite series expansion will come closer and closer to the actual function f of x. But it's always going to be closest at your pivot point. Now, a good solution to this is, well, if I kept going, it gets closer and closer to fitting my curve. So if I went to infinity, supposedly, it would match perfectly. So let's do it. So this is called a Taylor series expansion. And a Taylor series always has to be relative to some function. You're doing the Taylor series on a function. And it's f of x, this is about some point x equals a, is equal to the sum, as n goes from 0 to infinity, of the nth derivative of the function over n factorial times x minus a to the n. And actually, this should be the nth derivative of the function at a. So you're going to evaluate the function at each one of those points a. You're going to take the displacement of your x-coordinate from that point, but you still do have an x in your final result. So that's the value that's actually getting these x's plugged in when you're done and you have your infinite series expansion. So let's use an actual example, because this is all very theoretical and we've got this formula here. Let's actually see it in action. So let's say I wanted to do f of x equal to sine. Let's say I wanted the infinite series expansion for sine. And let's say I wanted to do that about the point pi. So first things first, since in this expansion we're going to have the nth derivative of this, and that's going to keep going on and on, let's take a few derivatives of this function. And I'll do that over here. So of course the zero derivative, or just not the derivative of all, of the function is equal to my function sine. The first derivative of sine is cosine. The second derivative, well, if you do the derivative of cosine, you get negative sine. Let's do the third derivative. You do the derivative of sine, you just get cosine, but now there's a negative in front of there, so negative cosine. And if we do one more, so let's say we do the fourth derivative, the derivative of cosine is negative sine again, but now you have negative times a negative for positive. And actually from here on out, as you go, this is just going to cycle through that. Sine, cosine, negative cosine, sine, cosine, negative cosine. So once we recognize this, we can do as many terms as we want of this pretty easily. Now let's actually plug in the pi values, because notice up here in the Taylor series, you're plugging in the value there into the function. So f of pi is equal to sine of pi, which is 0. F prime of pi is equal to cosine of pi, which is equal to -1, and so on. Notice every time I have a sine, I'm going to get 0. When I have a cosine, I'm going to alternate. Cosine of pi is -1, just like it was up here, but because this is negative cosine, we get a positive one. And again, this is just going to start cycling. Okay, now let's actually write out the series. So, according to the Taylor series formula right here, this is going to be the sum as n goes from 0 to infinity of, I'll keep the f of n notation for now, f of n of pi over n factorial times x minus pi to the n. Now let's start writing out some of these terms. So when n is 0, I'm going to get the 0 derivative of the function, so just the function as is. So that's going to be sine of pi over 0 factorial times x minus pi to the 0. Then I'm going to get plus, well now the first derivative, n equals 1, so that's cosine of pi over 1 factorial x minus pi to the 1. Now I have n equals 2, so the second derivative is negative sine. So this will be negative sine of pi, 2 factorial, x minus pi squared. Now I'm up to n equals 3, so plus a negative cosine of pi over 3 factorial, x minus pi cubed. And of course, we can keep going with this. I'll go out the one more term since we have it. So if n equals 4, we're going to have plus sine of pi again over 4 factorial, x minus pi to the 4th. So while this is evaluating the Taylor series, you've got the nth derivative of the function times pi over n factorial x minus pi to the n. The reason we'd want to write all this out is some stuff is probably going to drop out of this, considering we have zeros over here. And so maybe we can rewrite this in a much simpler way, considering what function we actually have. So it's always important when you do your Taylor series to write out enough terms, look at what happens, and see if there's a simpler pattern going on than just the basic Taylor series expression. So if I look here, sine of pi is 0. So all these terms that have sine of pi are just going to drop out entirely. That's gone, and that's gone. So if I rewrite it, we've got cosine of pi, which is -1. 1 factorial is just 1. So this is just a negative x minus pi to the 1. Okay, what's my next thing? Well, we've got plus a negative cosine pi. Cosine of pi is -1. So negative is positive. And we've got over 3 factorial. So this is going to be plus 1 over 3 factorial times x minus pi cubed. And if we had done another derivative, right, know how this cycles? The next one after sine would be cosine again, and my n would be 5. So following this pattern, I'd have minus 1 over 5 factorial x minus pi to the 5th. You can verify that for yourself. Just take the derivative again, write it out like this. You should reduce down to that. And so now if I look at this, I can write it way simpler because I just have x minus pi to 1, 3, 5. Next one will be 7. Odd powers. I have division by odd factorials. Notice over here it would be 1 over 1 factorial, which is just 1. And I have alternating signs, negative, plus, negative. This next one would be plus, and so on. So to write this as my final answer for a Taylor series, it would be the infinite sum as n goes from 0 to infinity. We're going to have a -1 here. The first one is indeed negative, so since n starts at 0, I'm going to do n plus 1 So that'll give me negative 1 to the 1, which gives me that negative. The next one would be into the 1. Negative 1 squared would be positive 1, so I get a positive, and then that pattern's going to continue. Then I'm going to have my x minus pi to, okay, n plus 1 again, right? Because it goes 1, 3, 5. And it's actually not n plus 1. It's going to be 2n plus 1. Because these are odd powers. And so to be an odd number means that you can be written as 2 times something plus 1. So when n is 0, 2 times 0 is 0 plus 1 is 1. When n is 1, 2 times 1 is 2, plus 1 is 3. When n is 2, 2 plus 2 is 4, plus 1 is 5, and so you can see that pattern's carrying on. And in the bottom, we have the same number as a factorial. So that's just going to be 2n plus 1 factorial. So there we go. The Taylor series expansion for sine of x about the point a equals pi is going to be this. And we did that just as an example of how to do the Taylor series expansion. And just as a reminder, what's going on is we have the function sine of x, and over at pi, we want to write it out as just a sum of polynomials, and we want to approximate it as best we can. And you can see that's what we've got. Pi is just a number. These things in front are just numbers. So I've got x to a power plus x to a different power plus x to a different power with some coefficients. So this is just a bunch of polynomials. There's no trig function there anymore. But if I go off to infinity, this is going to match onto the sine function. So I've written a trig function in terms of just your everyday like algebra functions, which is pretty cool. The final thing I want to point out is that there's what's called a Maclaurin series. And all that is you're just going to do your infinite series expansion about the point a equals 0. That's where you're going to start. So if I put that here, a Maclaurin series is just all that for a equals 0. So there we go. That's a discussion of Taylor series. A Maclaurin series is just an easier to calculate Taylor series, really, what their purpose is, and just a reminder that when you write this out, you should look for things that cancel and see if there's a simpler way to express it from here to here. And that was today's topic video.